Good morning, everyone. Let us start this session. So, in the last lecture, we have seen the classification for the fluids. Okay. So, classification is based on the Newtonian and the non-Newtonian fluid. So, the basis for this classification is the Newton's law of viscosity. So, Newton's law of viscosity, its mathematical equation is the shear stress drop. This is equal to mu into du by dt. Okay, that means the shear stress is directly proportional to the rate of deformation or the rate of strain, shear strain. Okay, so this is the rate of deformation. So the rate of deformation is mathematically given by this equation d theta upon dt. Okay, so this d theta upon dt for the fluid, this is called as a rate of shear strain. Okay, and in case of solid, it is just an shear strain because solid has a permanent deformation, and after specific angular deflection, the solid will stop its deformation. Okay, but in case of fluid, the deformation is a continuous, so you can observe the continuous flow of the fluid. So we give the rate of deformation as a d theta upon dt, and this is equivalent to the velocity gradient, which is a du by dy. Okay, and therefore we write tau is equal to mu into du by dy, where mu is the viscosity. Now, based on this equation, we classify the fluid as a Newtonian and the non-Newtonian fluid. So, fluids which follows or obeys this law, they are called as Newtonian fluid. So, if you draw the graph of shear stress versus this velocity gradient, or this is called as a rate of deformation. So, this is the rate of deformation. Then, for the Newtonian fluid, we will get the straight line graph. So, this is the Newtonian fluid. Okay, and if you draw the slope of this line, then this slope will be the dynamic viscosity, which is the constant mu. Okay, now some fluids do not obey this law. Okay, so these are called as a non-Newtonian fluid. So in that, the first is the shear thickening fluid. Okay, so for the shear thickening fluid, we get the graph like this. So what is meaning of shear thickening fluid? So first one, which is a non-Newtonian fluid, which is the shear thickening fluid. Okay. So here in the shear thickening fluid, as we increase the stress value or the force value on the fluid, so if we increase the force value or the shear stress value, then the fluid will become more and more thick. Okay, that means its viscosity, it will increase. So that you can see here on the graph. So here on the graph, you can observe if you draw one tangent line at different points for the non-Newtonian fluid, which is a shear thickening fluid, then as we go on increasing the shear stress, the mu value, it will go on increasing. Okay. So this is called as shear thickening fluid. So here in the shear thickening fluid, we have the example of cornstarch solution. Okay. So cornstarch solution in the water. So it will become hard as we increase the force on the fluid. Okay. And at the small value of force or small value of shear stress, it is the liquid state. Okay. So in the last lecture, I have shown the video for the shear thickening fluid. Okay. Second type of the non-Newtonian fluid, this is called as shear thinning fluid. Okay. So shear thinning fluid. So shear thickening fluids are called as a dilatant fluids. Okay. So these are the dilatant fluids, and shear thinning fluids, these are the pseudoplastic fluids. Okay, so for shear thinning fluids, you can observe this graph. This is for the shear thinning fluid. The meaning is, if you increase the stress value, that is the force value on that fluid, the fluid, it will become thin, okay, and it will start flowing. So here the example for the shear thinning fluid is the ketchups, that is a tomato sauce. Okay, so this is the best example for the shear thinning fluids. Then the paints, that is oil paints, these are also shear thinning fluids. Okay. So here you can observe on the graph what is the meaning of shear thinning fluids. Okay. So here, if you select the different points, so first I have selected at the low stress value, at some moderate stress value, and at the high stress value. Okay. So at these 3 points, if you draw the tangent line, then you will get the slope. Okay. So here, the slope, it will give the value of the viscosity at that point. So at the low stress value, you can get the tangent line. Okay. So this is the steep tangent line. So it will have the high slope and therefore the high viscosity. Okay. Then at the moderate value, viscosity will be low. And this is the very low value of the viscosity at the very high value of the stress. Okay. That means as we increase the shear stress value, you will get the decrease in the viscosity. Okay. So that will increase the fluidity of that fluid. Okay. So let us see this. So I will show the video for the shear thinning fluids. Okay. Okay. So here you can observe for the tomato ketchup, initially, if the force applied on the bottle is low, then it will behave as a solid. Okay, so here we are not applying the force, and as we suddenly increase the force, okay, then you can see it starts flowing like a normal fluid. Okay, and therefore this is called as shear thinning fluids. So oil paints also behaves in the same manner. Okay. So here you can see we have just kept one object on that ketchup. Okay. So here it behaves almost like a solid. Okay. So this is the low stress value. So at the low stress value, you can see the ketchup is almost like a solid. So it is the highest viscosity. Okay. And if you drop this object from certain height, then that will cause the impact and it will increase the shear stress value. So then the fluid will behave as a liquid. So here you can observe. Okay, so this is the highest value of the shear stress. Okay, when we drop the object from a certain height. So here fluid suddenly becomes thin. Okay, that is viscosity decreases. So here you can observe. Okay, and this is called as a non-Newtonian shear thinning fluids. Okay, so and next type we have the Bingham plastic. So in the Bingham plastic, up to certain level of the shear stress, we cannot observe any fluid motion. Okay, and after specific value, this is called as a limiting value. Suddenly, that fluid it will start flowing as a normal fluid. So this line, it will be similar to the Newtonian fluid. Okay, but up to this point, you cannot see any motion in that fluid. Okay, so for the Bingham plastic, the example is the toothpaste. Okay, so we'll show the video how the Bingham plastic fluids behaves. So here you can see. So initially, if you apply the low value of force or the shear stress, you cannot see the toothpaste is in motion or the flowing. Okay, and suddenly, if you increase the force value beyond the certain limit, okay, then you can see the flow. Okay, so this is called as a Bingham plastic fluid. Okay, so these are all the classifications for Newtonian and the non-Newtonian fluid. Okay, and we have seen the examples and also the mathematical equation beyond the classification. Okay. So the total classification, it is based on this graph, shear stress versus the rate of deformation or the velocity gradient du by dy. Okay, so now we will solve some of the problems on the Newton's law of viscosity. Okay, so note down the problem. We have the plate of 0.025 millimeter distance from the fixed plate. and it moves with the velocity 60 centimeter per second, and that requires a force of 2 Newton per unit area, 2 Newton per unit area. Okay, so it is 2 Newton per meter square to maintain this speed. Then determine the fluid viscosity between the plates. So determine the viscosity. Okay. So we have seen the derivation for the Newton's law of viscosity. So in that derivation, we have assumed one plate. Okay, so it is kept on the liquid. So this is the fixed plate, and this is the moving plate. Okay, so moving plate, if we apply some force, then it will start moving with certain velocity. So this is the v velocity, and this is the liquid or the fluid between the two plates. Okay, so here what is given? The moving plate, it is having the velocity v, which is equal to 60 centimeter per second. So this is equal to 0.6 meter per second. Okay, and the distance between these two plates, so this is the 0.025 millimeter. So this distance, this is equal to L, or this is equal to D1. Okay, so this distance is 0.025, this is millimeter. So convert this in meter. So it is equal to 0.025 10 to the power -3 meter. Okay. Next is force for upper plate is given. Okay, and it is given as a Newton per meter square. So this value is not a force. Okay, so what is given? This stress is given. So shear stress value, this is equal to, so this is tau, this is equal to 2 Newton per meter square. So directly the shear stress value is given. Okay, and the question is we have to find out the viscosity or the dynamic viscosity for the given fluid. So for this fluid, we have to find out the value of mu. Okay, so we will use the Newton's law of viscosity equation, which is shear stress is equal to mu into velocity gradient, which is a du by dy. Okay, so this du by dy, this value, so this is called as a velocity difference. So this is the velocity difference, and this is the height, okay, or the gap between the stationary plate and the moving plate. So the velocity difference will be, so at the bottommost layer, which is in contact with the stationary plate, this velocity will be 0. Okay, and velocity will increase from bottom plate up to the top plate, and at this point velocity will be maximum, which is equal to v. So we get this velocity triangle. So this is the highest velocity, and here velocity is gradually reducing like this. Okay, so this velocity, sorry, this is u, this is equal to 0. Okay, at this point u is equal to the maximum velocity. So du, that is a difference in the velocity, this is equal to velocity v minus 0. Okay, so this is equal to 0.6 meter per second. So from this you can write tau is equal to, so tau value is given, which is a 2, mu is unknown, du is 0.6, and the dy means gap between these two plates, which is 0.025 millimeter. So in meter it is 10 to the power minus 3. Okay. So this is equal to mu. So just calculate the value of mu. So this is 8.33 into 10 to the power minus 5 Newton second per meter square. Okay. So this is the value of the viscosity for the liquid between the two parallel plates. Okay, right to the next problem. So calculate the dynamic viscosity of an oil which is used for the lubrication between a square plate which is used for the lubrication between a square plate and its size, this is 0.8 by 0.8. So this is in meter. So this is a meter square, and an inclined plane having the angle with angle of inclination theta, this is equal to 30 degree. Okay. The weight of the square plate is 300 Newton. The weight of the square plate, which is 300 Newton. And it slides down the inclined plane with minimum velocity so that velocity is 0.3 meter per second. The thickness of the oil film is 1.5. Okay, so this is the given condition. So this is the inclined plane. This angle is theta. Okay, and there is one plate. Okay, and between these two plates, we have the lubrication, which is the oil. Okay, and this plate, it moves in the downward direction with the velocity, which is 0.3 meter per second. And this gap between the two plates, or this inclined plane and the plate, this is equal to 1.5 millimeter. Okay, so we have to find out the dynamic viscosity. So question is find out the mu value. Okay, so we have the equation tau is equal to mu into du by dy. Okay, so now we have to find out the shear stress which will act on the layers of the fluid. Okay, then the du by dy, which is the velocity gradient. Okay, so du by dy you can directly find out. So du by dy, this is equal to, so here maximum velocity we take as a v minus the velocity at the bottommost layer, and dy is nothing but the thickness of the film. Okay, so here v, which is 0.3. Okay, so this is the velocity at this point. Velocity at this point, it will be 0. Okay, so this is your velocity triangle. So 0.30 upon thickness is 1.5. This is millimeter, and 0.3 is meter per second. Okay, so here v is 0.3 meter per second. Thickness p, this is equal to 1.5 millimeter. So it is 10 to the power minus 3 meter. Okay, so put all these parameters in the SI unit. Okay, so from this you will get the value for the velocity gradient, which is the du by dy. Okay, so just take the value for du by dy. So this is, so it is 0.2 into 10 to the power 3. So this will be 200. Okay. Then next we have to find out the shear stress value, that is the tau value. So the basic formula for shear stress is actually this square plate. It is having the dimension. So I will draw this in a 3 dimension. So this is the given square plate. So it is having the dimension 0.8 by 0.8. Okay. So this area, so actually this area will be the contact area with the fluid layer. Okay. So the shear stress will act in on this complete area. Okay. So this shear stress we can find out as the shear force upon the area of the plate. Okay. So tau is equal to force upon the area, which is a shear area. So this is equal to, now force is not given. Okay. So what is the force value here? So you can observe the weight of the plate is given. Okay. So this plate, it is sliding down the plane just due to the self weight. There is no external force. So this self weight we need to resolve in the direction of the plane. So this is the point. Suppose this is the center of gravity. So this is the weight vector. So this is the W. It will act exactly in the Y direction. Okay. But this complete W, it will not cause the sliding motion. Okay. So we have to resolve this along the plane. So this component only will cause the motion in the downward direction. And there is one more component, which is the component perpendicular to the plane. Okay. Now here we have to find out the angle, so that we can find out this component. So this angle is theta, which is a 30 degree. Okay. Now this angle, so this is a 90 minus 30. So this will be 60 degree. Okay. Now observe this triangle from this point. So in this triangle, again, this is 90 degree. So this is 60. So this angle here, this is 30 degree. Okay. So this component, that is a component along the plane, this is equal to W sine 30. And this component will be W cos 30. Okay. So only W sine 30, it will cause the motion in the downward direction. So for the F, we will just consider W sine 30. So this is the shear force. Okay. So this W cos 30, it will act on the plate. So F is equal to W sine 30 upon the shear area is 0.8 into 0.8. So W is given as a 300. This is sine 30. One, this is 0.64. So the 300 sine 30 is 150 upon 0.64. Okay. So let's calculate this value. So this is equal to 234.37. This is Newton per meter square. Okay. And now put the value in this equation. Okay. So finally you will get mu is equal to, this is tau upon du by dy. So this is equal to 234.37 upon the du by dy is 200. Okay. So it is 1.17 Newton second per meter square. Okay. So sometimes the question will be find out the dynamic viscosity in terms of poise. Okay. So you should know the relation between the poise and the Newton second meter square. So 10 poise, this is equal to 1 Newton second meter square. Okay. So just multiply the Newton second meter square by 10. You will get the value in poise. So here mu is equal to 11.7 poise. Okay. So sometimes the viscosity is expressed in terms of poise. Okay. So just remember this relation. 1 Newton second per meter